Alrighty, so today we're going to be talking about Charles' law. So as you may know, there are three gas laws: Boyle's law, Charles' law, and the combined gas law. There's actually a couple more, but we're not going to be dealing with those right now. So for Charles' law, the important thing to know is that temperature is related to volume. Remember, when you have a solid, your particles are only moving a little bit back and forth in their space. When you have a liquid, they're rocking a little bit more side to side. Okay, they're going a little further, they're vibrating a little bit more. Then when you have a gas, they're running all over the place, and you've got these molecules running all over the place. So the more energy you add, remember, you go from solid to liquid to gas, and the more energy you add, the more the molecules move. So the more they move, the more they're going to bounce around. The more they bounce around, the more they're going to want to expand your volume. So with Charles' law, we have an example here. This is a balloon on top of an Erlenmeyer flask. Okay, these little funky flask guys, they're called Erlenmeyer flasks. So we start out with our balloon on top of our flask. And the thing with our balloon is that our balloon is not full of air. We actually figured out a way to make it so that there's absolutely no air whatsoever in this balloon for our beginning. So we know that our volume, when we say that this is a 150 milliliter flask, we know that our volume is actually going to be a little bit more of that. So if this whole thing is just full of air, and we've got as little air as possible in this balloon, we'll say that our starting volume is actually 175 milliliters. And we're going to say that we start with a temperature of 0 degrees Celsius. Pretty cold, right? 0 degrees Celsius, that's where water freezes, turns into ice. Okay, so pretty cold. So now what we're going to do is we're going to add some heat. We're going to heat up this gas. When we heat up the gas, we go from walking kind of slow to getting a little faster. And all of a sudden now we're running full speed. So when we are talking about that, we mean that the molecules move faster and faster and faster and faster the more heat we add. So if the molecules are moving faster and we're not controlling the size of the container, like we're not keeping it compressed, that means that the molecules are going to take off all over the place. They're going to try and make it as big as possible. So we're going to increase our volume. So over here, we're going to say that we know that we're going to increase our temperature to 100 degrees Celsius. Okay? And we want to know how big it's going to be. So how do we solve this? Now, here's the tricky part. With our Charles law, we are actually relating volume and temperature. When temperature goes up, volume goes up. Now, here's the thing. With our gas laws, we typically use multiplication and division. And if you multiply or divide a negative by a negative, you wind up with a negative. Now, is it possible to have negative degrees Celsius? Of course. Every winter, we always get down to like -5 or -10 degrees Celsius, depending on what part of the world you're in. Up here in the Northeast, it can get down to way below 0 degrees Celsius. So when we have those negative signs, that's really bad for the math here, because can you have a negative pressure? Not really. Can you have a negative volume, like negative milliliters? It doesn't really work that way. So when we're doing our math, we need to make sure that we don't have the negative. So the way that we do that is we use a type of temperature called Kelvin. So what we do to convert to Kelvin is very, very easy. What we do is we take our temperature plus 273 is equal to our Kelvin. And you can't really read that, so what we're going to do is we're going to rewrite that bigger. Our temperature in degrees Celsius plus 273 equals Kelvin. Okay? So here's what we are going to do. We are going to go ahead and erase all this, and I'm going to write down our volumes, and we will use this space for our equations. So like I said, we are going to be starting off with a volume of 175 milliliters. Our first temperature is going to be 0 degrees Celsius. Now we want to find our volume too. We don't know that yet. And we have our temperature too is 100 degrees Celsius. So first things first, we're going to need to convert those pesky temperatures into Kelvin. So really simple, we just add 273. So that gives us 273 Kelvin for temperature 1. We add 273 here. So we get 373 Kelvin for temperature 2. Okay? So now we need to use Charles' law. Charles' law itself is V1 over T1 is equal to V2 over T2. So what this means is that if our temperature goes up, our volume goes up. If our temperature goes down, our volume goes down. And we will get through how to solve for temperature in just a moment. So let's take what we've got here. We know that our volume 1 is 175 milliliters. Our temperature 1 is 273 Kelvin. Our volume 2 is unknown. Our temperature 2 is 373 Kelvin. So what we're going to do is we are going to substitute those into our equation. So what goes in for V1? Well, that would be 175 milliliters. What goes in for our T1? That would be our 273 Kelvin. And we're going to say that equals what goes in for V2, we don't know. So we're just going to leave that as V2. And what goes in for our temperature, that would be 373 Kelvin. So now what you need to do is you need to divide this by this. So we're going to divide this by this. And that will give us, one moment please, that will give us 0.6410 ... Now it's best practice when you're using this in your calculator, just leave this value in there. You want to leave as many digits to the right as you can, because if you round at this point, it could potentially make your number incorrect, your final answer incorrect. So we've got that, and that's equal to V2 over 373. So now what we need to do is we need to get this off the bottom. So what we're going to do is we're going to take this, since we're dividing here, we're going to multiply on this side to get rid of it. So we take this over here and we multiply. So when we multiply that, what we wind up getting is 239. Now we need to remember our units. So what are we looking for? We're looking for volume. What was our original volume measured in? It was measured in milliliters. So what will our unit be here? It will be milliliters. Okay, so that's how you solve a pretty straightforward, simple one where you're looking at finding the volume. When it comes to finding temperature, it's a little bit more complicated. So let's take an example. All right, so let's say now that we know what volume we want this to get to. So we've started out at our same spot. We're still at 175 milliliters, still at 0 degrees Celsius. Now we want to increase our balloon size to 400 milliliters, and we want to know what temperature it would have to get to for us to do that. So our V1 is still going to be 175 milliliters. T1 is still going to be 0 degrees Celsius. V2 is going to be 400 milliliters. T2 is going to be question mark. So here's what we would do. First things first, always convert to Kelvin. Okay? So we add our 273, which means that our T1 is 273 Kelvin. Obviously, we don't know our T2, so we can't add 273 to it. We'll get to that in a minute. So now, here's the funny part. Temperature is on the bottom. So we can't really solve for it being on the bottom, at least not easily. The best way to do this is to flip both sides. So now instead of having V1 over T1, we now have T1 over V1 equals T2 over V2. Now, it is essential that if you do this, you need to remember that what you do to one side, you must do to the other. If you flip the left side, you must flip the right side. Always make sure you do this, or else you will get the incorrect answer. So, here we go. So what goes in for T1? Well, that would be here, obviously. We're going to take our 273K, put it up on top. So I've got 273 Kelvin on top. What's our initial volume? It is 175. Over on our right-hand side, we've got our T2. So we don't know that, so it's just going to go as T2. And what's our V2? It is 400. Alrighty, so now we are going to do our math, where we take our 273 and divide it by 175. So that is going to be 1.56. Now this one is actually just 1.56 straight up. No decimals, no repeating, no anything. So you would write down 1.56 at this step. And that is equal to T2 over 400. So now, again, 400 is on the bottom. In order to get it off the bottom, we need to multiply the left side by that 400. So it turns out that 1.56 times 400 is 624. Now what unit is our temperature always going to be in? It's going to be in Kelvin. So this is going to be our T2. Now most people don't use Kelvin on their day-to-day lives for their temperature readings and how they would measure temperature. So we actually want to figure out what this means in regards to temperature in reality. So 624 Kelvin, and if we added 273 to go from Kelvin, or from Celsius to Kelvin, we're going to subtract 273 to go from Kelvin to Celsius. So that's minus 273 equals, and that gives us 351 degrees Celsius. So you'd have to get that balloon pretty darn hot to get it to be about 400 milliliters. And I bet you the rubber would probably break before it got that big. But this gives you an example of how you would solve Charles' laws both ways. What we are going to do next is we are going to do a brief primer on the combined gas law. So be with me in just a moment.